All right. Hello, everyone, and welcome to the first of our virtual meetups for the Central London Data Science meetup. Now, hopefully, a lot of you have joined the Slack channel as well. So if you haven't done that already, please use the bit.ly link at the start to join. Those of you that are already in the Slack, what I'll be doing, I'll be monitoring the Slack throughout. So that's how we'll be able to ask questions and stuff like that. So anybody who's in the Slack channel, please ping, message, put an emoji or something so I can see. Be very cool. We got anyone in the Slack yet? There's a bit of a delay. So there's maybe like three or 4 seconds. Okay, awesome. So we're seeing people in the Slack. This is awesome. Cool. All right, so let's get started. We're all here to learn about precision recall and pneumonia, hopefully. And we're kind of running this like we do our normal meetups. We assume beginner level knowledge, but we're going over some topics that even senior data scientists get confused with. Like we're talking about precision recall today, and if anyone's ever used that before, you'll know it's a very wordy topic. There's a lot of easy ways to get mixed up. So we're going to be going gently through all that and doing some practical implementation of it by trying to predict pneumonia in X-rays. So let's get started here. All right. What is so cool about optimizing precision recall? Hi, Karen. Well, when you optimize precision recall, you can make bad models actually sometimes pretty useful, and you can make models that are already performing well even better. So this is obviously, if you've never heard of precision recall yet, you have no idea like how that's possible. We're going to be going through that. And this process of optimizing precision recall is incredibly important when you're building models that have to make very serious decisions, like in medicine, for example. All right, we've got 3 questions that if you don't know how to answer yet, we hope that you'll be able to answer by the end of the workshop. Number 1, what is precision recall? What do you need to think about, or when do you need to think about precision recall? Like what kind of problems? And the final question is, how do you actually go about optimizing your models for precision recall? And this is all, as you'll see in the examples, it's very much application driven. Like you need to know what specific problem you're trying to solve. All right, let's get into this. Okay, what do you need? Okay, right now, all you need is you need to be watching this YouTube, obviously, and then if you're in Slack, you really need to be in Slack because that's how you're going to be asking your questions. And most importantly, that's how we're going to share with you the resource links for the coding challenge that's going to come along later on. So let's look a bit about who we are. So I'm Zach. Me along with Blair and Palong, we help run this meetup group. We're all kind of self-taught in machine learning and data science by going to these kind of meetups and doing these kind of workshops online. And later on in the evening, as you'll see, we're actually going to have, well, we're first going to start with a 50-minute talk about the precision recall and all the theory. Then we're going to get into a really nice, juicy practical, which we've got set up for you, along with some really cool kind of interactive tools that we've built specifically for this meetup. And then we're going to actually end with a hangout. So anybody who's free can jump on a call, and we're all going to be in the same call and just chatting about like what we did, maybe what we learned, or what kind of data science machine learning problems you're facing. And yeah, it could just be social. It could be anything. How your day's going, that kind of stuff. You know, we expect like everyone's probably at home now. So yeah, that is the plan. Hopefully a few of you can stick around for the hangout at the end. What we'll do now, we'll jump right into this. All right. So what is the problems we're specifically talking about? So here's a rough diagram of the machine learning ecosystem. So this is one where we're looking at, if you've ever done any kind of machine learning, you might see some of these terms and they might be familiar to you. Oh yeah, one more thing is, let me just go back here. Blair and Palong, they're in the chat as well. So they're in the Slack channel. So I'm going to be going through these slides, and I'm going to be also watching Slack and try to answer some of your questions on the fly. They're also in the chat. And so if they can answer your questions as well, they're going to be helping you with that. So yeah, don't be afraid. We've got a little teacher emoji in our Slack. That's how you'll know it's either Blair or Palong or us. All right. The machine learning landscape. You've seen a few of these. We've got reinforcement learning up here. If you haven't seen any of these, that's fine. We're going to be going through them, but we're only going to be going through a couple of them because this is what we're focusing on today. So we're going to be focusing on a supervised learning problem. That is like the quintessential machine learning problems where you've got some input data and you're trying to predict some output that you know of. So you've got, in our case, it's going to be an image of pneumonia and predicting some output, which is going to be if it's pneumonia or not, like that kind of label. Within supervised learning, we're going to be focusing on classification. That is, we are predicting a distinct set of the labels. So we're predicting pneumonia or not pneumonia. In the case of regression over here, in fact, there's a regression over here, that is predicting a continuous number. So we're not doing that today. We're just looking at a classification problem. And then even more specifically, we're focusing just on binary classification. So that is when we're predicting a 1 or a 0. And we'll go through a bit about this. If you've never done this before, don't worry, we're going to be going through it nice and slowly. But yeah, so a lot of the stuff we're discussing here about precision recall also applies to this guy over here, multi-class classification. That's when you're predicting from a set of multiple labels. So imagine an image, and you got to predict if there's either a car, a boat, a truck, or a bike in it. That's an example of multi-classification. We're not going to be focusing on that today, just because the same stuff applies to it, but it confuses things a bit. So we're just going to be focusing on binary classification. If you've got questions about any of these other topics, feel free to join in in the Hangout at the end where we can discuss other things. All right, so we're going to be approaching this, and we're going to be assuming beginner level knowledge. So assuming you've got some idea of what machine learning is. I'm aware that quite a few of you will also be experienced in machine learning and data scientists yourselves. So forgive me if I'm going through the first bits a bit slowly. So we're going to be getting everyone up to speed with supervised learning and binary classification first. So supervised learning. We start off with input data and output data, and we try to learn the pattern between the two. In our example, we're working with images, so our input is going to be an image of an X-ray. And the output is going to be, in this case, the label pneumonia. Another example of input is the same image, but the output would be normal. So again, because we're doing binary classification, there's only 2 labels. So this is an example of the data structure for supervised learning. So each of these is an example, and we have an entire data set of examples. So we've got our whole data set here, and we're going to split it. We've got training examples, and we have test examples. Now, why do we split it? Well, we take our training examples and we feed that to our machine learning model. And that is the data that the model will actually look at and try to learn the pattern between the input. Like, how do I get from this image to this label? And it's going to learn that and stuff. With our test examples, we're going to take just the input data, so in our case, just the images, and we're going to feed it to our model, which should have learned something about the problem, and it's going to try to make its prediction. So it's going to think, it's going to try to get as close to what it's learned as possible. So that was just using the input from our test data. What do we do with the output? So we still have the outputs, and because our model has made predictions, we can actually use those outputs because we know those are the correct answers and see how well our model did. So this is really key because this is what we're going to be using a lot later on when we're talking about misclassifications. We're going to be using test data to work out how well our model is doing. So in this case, we can see, oh, our model is about it gets 3/4 of the answers correct. So we can say it's about 75% accuracy. Yeah, remember, this is really key because a lot of precision recall it's a metric, a bit like our accuracy metric we're using here. And so whenever we're discussing these metrics, we're talking about their scores on test data. We're talking about scores on data that the model doesn't know, hasn't seen before, but we still have the correct answers. And that's how we're able to determine if the model is doing misclassifications or not. So that's what we do with test data, and we're going to be looking at that later on. That's supervised learning. Binary classification, this is real quick. Anytime, I've already covered this, anytime it's a 1 or 0 problem. So we've got cat or not, pneumonia or not, or it could be anything. It doesn't need to be an image to be a binary classifier. If the output is a 1 or a 0, or can be kind of interpreted as a 1 or a 0, then it's a binary classification. Okay, should all be up to speed now. What's supervised learning? What's binary classification? All right, this looks a bit scary, but it's not. We're just examining a model, and you don't need to know how neural networks work for this workshop. But let's assume this is a simplified diagram of a neural network. We're feeding in an image to this model, to this neural network, and it's going to output. It's been trained to predict 1 for pneumonia and predict 0 for normal. So if this is a pneumonia image, what do you think the output is going to be? Can we get a poll in the chat? Let me see. Wait, I'll wait for the poll. All right, we've got one. Okay, some people are predicting no idea. Okay. All right. So that's completely reasonable. Some people say if it'll predict one. What it will do is it will predict something like this. Yeah. So everyone was correct in thinking that it would predict one, but actually, in a neural network, the output would be a continuous number. It wouldn't be a strong 1 or 0. Yeah. Some people are yeah. It was a trick question. So yeah, the output wouldn't be a strong 1 or a 0. It would be something like this, which you'd be completely right in interpreting as a 1 or a 0. Because naturally, what you would do, if someone said, "Is this a 1 or a 0?" You'd be like, "It's closer to 1, so we assume 1." That is exactly how we then interpret it. So built into, for example, the software we're using later on, Keras, they actually have a function called predict classes. And that will automatically say whichever one it's closer to, it will predict as a 1 or a 0. And this is like the kind of code it has behind the scenes. It's got a little thing. If it's greater than 0.5, predict as 1. Less than, predict as 0. This is crucial right here, where the understanding that the raw output from the model is not just a 1 or 0. It's actually, it's kind of like a confidence, not really. And it's kind of like a probability, but not really. It's like a signal strength. Like, it's got a lot of signals saying that it's probably pneumonia. Again, I used the word probability there. It's not a true probability, but it's like a signal strength. You can kind of use it practically as probability. All right. So let's imagine we've got our test data and we feed it through the neural network and we plot out its confidence signal scores here. All right, this guy came in. He's green. We know this person actually has pneumonia because it's our test data. And I'm representing that as a green emoji. But it's predicted pneumonia strength as like 0.9. That's the signal that came out of the neural network. Okay, that's good. We would have correctly got that one correct. Next one, they didn't have pneumonia, but our model also suspected they didn't, which is good. All right, this one, closer to the midpoint, but it still got it right, which is good. This one also close. You can imagine then we might get some wrong. This one, there was a bit of noise in the data. The training didn't go on long enough. The model got it a bit wrong. This one got it wrong. They thought it didn't have pneumonia. We feed through our entire test data, and this is likely what you're going to see. You're going to see data where you've got all the very kind of confident ones off to the end, and then around the middle point, you get the less confident ones. All right, what do we do? This is how our model works. This doesn't really mean anything to us yet. We can see that we're getting some wrong, but what we need to do is start thinking about the application of our model to determine if this is appropriate behavior. So let's think of an application. We have a robot doctor, and I appreciate the design skills I put into this. We have a robot doctor that will automatically dispense very important medicine. It's using the model that we built, and we now need to think about the impact of the predictions we're making. By the way, I don't recommend this as a real project for anyone to build. Here we go. So we've got a column for when we predict things to be pneumonia and a column for things when we predict them not to be pneumonia. All right, this person, they predicted to be pneumonia, and as the emoji shows, they actually did have pneumonia because we're using our test data. This is good. Great. We don't need to consider this. Like, yeah, good. We're predicting pneumonia when it is pneumonia. Bottom right, this is the easy one. Yeah, again, we're predicting them to be normal, and they are actually normal. That's good. No considerations there. Yeah, that's good. That's what our model should be doing. Now we need to think about when it's doing stuff that it shouldn't be doing. We predicted normal, but they actually did have pneumonia. In this instance, that's fine. We say, okay, they'll see a human doctor later on if it gets worse, and in this imaginary scenario, that's an okay thing to happen. Now we consider what happens if they get predicted with pneumonia, but they don't actually have pneumonia. Okay, this is terrible in this instance because it turns out the medicine that the robot would automatically administer it has side effects and stuff. So in this case, that's bad. So we say if you predict them to have pneumonia and they don't, that's very, very bad. All right, let's think about how we can change what we're looking at now. So this, remember that that if statement, that decision threshold that the Keras API has, where it says like if it's closer to 1 or closer to 2, that's set at 0.5, but we're able to set it to whatever we want. So what we can do here for this application is we can just move it. So if we move this decision threshold and say, okay, only predict things to be pneumonia if they're greater than, say, like 0.9, what kind of behavior would that create? So let's look. So we've got our robot. We're running the exact same model, but we've just changed that if statement at the end to be 0.9. Okay, we're gonna throw all our test data through, and we get something that looks like this. So we get a lot of positive indications of pneumonia that were correct. Quite a few that were pneumonia, but they got classified as normal. But we already said that was fine. And then a lot of things that were normal that were classified as normal, that's good. And we have this like one case where it's classified as pneumonia, but it wasn't actually pneumonia. And you can see that one case back here. You can see it was this fellow here. So what do we call what we just did? Well, we can say we made this model more precise. Well, what does that mean? It means like, well, this is the kind of behavior we wanted. We wanted it to focus on just getting the pneumonia predictions to be correct when we're making them. We need to come up with it's very wordy. This is where it gets really kind of convoluted. We got to come up with a metric to kind of judge how we're measuring how precise our model is. And we can do that quite easily. So we say, okay, take the total number of predicted pneumonia and the total number that were actually pneumonia. Remember, we're using our test data, so we actually know the correct answers, and that's how we're able to do this. We can calculate precision to be just 1 divided by the other, and we can just say, like in human terms, 94% of the time when I predict it to be pneumonia, it is actually pneumonia. And that's what we want. For our application, we want to absolutely minimize how many people are misdiagnosed with having pneumonia. We don't really work. You can see we're not even considering this side of the equation. We're just looking at when we do predict pneumonia, how accurate are we? And that is what precision is. Precision is just the ratio of correctly predicted positive cases. In this instance of our model, the positive case is pneumonia. If you take this test and you test positive, you have pneumonia. So that's what we call our positive case. That is kind of the case we're interested in. All right. Let's flip it a bit. So we now have a new robot. And instead of it administering medicine, it's now just going to send them off to like a pre-screening diagnostic and recommend them on to see an actual doctor. So in this case, no real dangerous thing is happening if they get misdiagnosed. So these guys are all good as well. In this case, if they get misdiagnosed as having pneumonia, that's fine. They'll see a doctor briefly and then they'll quickly be determined to be okay. But if they get predicted to be normal in this case, that's very bad. In this instance, them going off could make more people sick before they end up visiting the doctor again. So in this, you can see how it's the exact same model, but because we're deploying it in a different application, the scenario is flipped. How do we do this? For that one, well, you can imagine we just move it the other way. So we've lowered the threshold. So now there's only going to be one misclassification of pneumonia, and the rest of these are going to be classified correctly, except for all the yellow ones. But we'll see that here. So we set the threshold to 0.2, and this is what our kind of prediction graph looks like now. Still a good few, loads of people correct here. Only one misclassified here, and this quite a few misclassified here. Now, so I had to try to come up with a word to describe this because I don't know of the correct word. But I like to call this a thorough model. The previous one was a precise model. This one's a thorough model. This one gets all the pneumonia cases, or close to all of them. And if we're going to come up with a metric to define how thorough our model is, we can just look at the total number of these positive pneumonia cases and divide them by the total number of ones that we actually correctly found. So if you can imagine, if it's like you're trying to judge how well you clean a house, you want to be as thorough as possible. You want to get as much stuff as possible, collect as much stuff as possible. Thorough is a nice word. The actual word is recall. So this is how much of the pneumonia cases did we recall? We want to get as many as possible. Again, like you can see, we're not looking at all at these people. This is the interesting thing with these metrics, these precision recall metrics, is they actually ignore the results here. Anything could be happening with the normal cases, but we're not looking at them. When we're talking about recall, we're just saying, oh, how many of the pneumonia cases did we capture? We're not considering the ones that were normal and misclassified. Yeah, that's the kind of intuition behind recall. It's all about the ratio of the total positive cases. In this case, pneumonia is our positive case. If you test positive, you have pneumonia, and it's of the total positive cases, how many did you correctly predict? How many did you find? So that's recall. All right. So this little chart we've been showing again. Like, this is an insanely wordy topic, so don't worry if it's like getting confused in your head. But let's look at this. So this is the little chart I've been showing you. We can actually, this chart is actually used a lot in machine learning. So if we put an axis just there, and we put these words here, so we say, okay, everything on the horizontal, those are the actual labels. Remember, we're using our test data, so we know the actual values for this. So everything on the across the horizontal, that's the actual label. So all the pneumonia cases are here, all the normal cases are here, and the vertical axis represents what our model is predicting. We got when we're predicting normal on this vertical, and when we're predicting pneumonia. And this is called a confusion matrix. So aptly named, because I find it very confusing every time I look at it. And each of these quadrants has an equally confusing name. The top left quadrant, because we are testing positive for pneumonia and they are getting them correct, we say they are true positives. And the bottom quadrant is also an easy one, because they are testing negative for pneumonia, but they're also true. We call those our true negatives. This is where it gets interesting. Top right, they are testing negative for pneumonia, but it's wrong. So it's our false negatives. And the bottom left is they're testing positive for pneumonia, but they're wrong. So the false positives. Now this is the go-to kind of visualization for prediction, recall, precision recall, misclassifications. But you won't see it with emojis. You'll see it usually with numbers. And when you see it, depending on who builds the confusion matrix, oftentimes the labels on the columns can be different. So that's one thing you gotta watch out for. Is sometimes people like to put the model predictions across the horizontal, or so make sure when you're looking at confusion matrix, very carefully read the labels, because it will completely flip your understanding of it. So be careful of that. So we're predicting, in our case, we're predicting across the vertical, but some people do different things. All right. That is the speaking portion over. I went a bit over the 15 minutes. The next part is the practical. So hopefully we're now going to share a link with you for you all to go to a Colab notebook. And I recommend you set up your screen to be in this orientation. The Colab notebook is going to open up inside like a Chrome window. You don't need to install anything. But if you get it up onto, say, like the right-hand side of your screen, put this video in some other corner, and then also get the Slack channel down in one corner as well, so you can keep up to date with everyone. What we're going to do now is we're going to go through an actual practical exercise in building a prediction model for doing image classification, and also how you can examine the precision and recall in using the things that we've used, like the confusion matrix, and how you can then optimize it for depending on what way you're going to deploy your model. All right, so we're now going to wait for people to jump into the Colab link, which should be sent out to everyone. I'm going to go to it myself as well. Well, actually, I will have, this is the link as well if you just want to shoot in here. And whilst people are setting up for that, this is a special notebook, and you'll see when you open it, because when you open it, you should see something that looks like this. You're gonna open it. This is, in fact, I will zoom in, because if you're putting this video in the top corner, it might be a bit small. I'm gonna zoom in. So this is Colab. If you haven't used Colab before, It is a free way of running machine learning and data science code and things like that. It's a Jupyter Notebook environment. So it's Markdown interspliced with code cells. And the first thing you're going to do when you come into this notebook, wait for like a couple of people to get into it. Let me actually, I've got a special tool. All right. So the first thing you want to do is connect to it. There'll be a button at the top right hand corner, connect. And you're going to want to come up with a name for yourself. Ideally, if you're in Slack, please use a name that's similar to your name in Slack. Because what we've done is we've built a special tool that will embed itself into the Colab notebook that allows you to, whenever you submit certain sections, they'll give you immediate feedback as to if you are correct or not. But also allows us to see everyone's progress. So we're able to go through at the appropriate rate through the whole notebook. So make sure you go and give yourself a name. If you're in Slack, please use your Slack name, because then we can find you in Slack and help you. So yeah, we're gonna wait for a couple of people to sign up, and then we're gonna start going through. So I'm gonna sign up as well. I'm gonna be like, Zach, sure. But here's where, like, if you're gonna need to run anyway. If you are already an expert in all this and you just want to like whiz through the notebook, feel free to do that. If you're not, what we're gonna do is we're gonna go through bit by bit. I'm gonna walk through going through the whole thing. So by all means, if you feel like I'm going too slow, just feel free to go ahead. But yeah, so hopefully you get signed up. I can see like loads of people have checked in. That's amazing. That's the power of my little dashboard. And we're gonna start with an easy question. How you run these cells? You click the play button, or you can hit Control Enter or Shift Enter. So pick your poison. For this first question, I'm gonna be bold to get it right first time. We'll see. Oh no. What has happened? Okay, this first one I got wrong. Let me check something real quick. I forgot to test the first question. We can just ignore the first. Let's assume that one was correct. But anyway, some people got the first one right. Maybe it was none. Okay, let's ignore that. Okay, ignore the first question. We're going to continue on to downloading of the data. So I've created our images and our labels. And if you click the play button, it's going to download that. And what's really cool about the Colab experience, it's all in a virtual machine, so you don't need to download any actual data to your computer. So it will just download to this notebook. It's wait, oh yeah, someone just pointed out the answer's not 2, it's 4. Can you tell this is my first time streaming? Okay. You should have faith in your teacher. The answer to 2 plus 2 is 4. Well, I think we've all learned something. We've got our data, and we're gonna continue. We've downloaded it, hopefully. Next section, gotta specify. So this is where we downloaded the data, and if you want to see the data, you can click on the side panel here. And it can, you hit the refresh and you can see the actual data there. So if you're looking for the file name, that is the file name. So we'll put in pneumonia.obj. Yeah, import. See, oh, everyone's storming ahead. We got task 2 done. Oh, this is great. We've got loads of people. All right, I've imported my data. Cool. Got someone Ben is storming ahead. All right, we've imported our data, and we're going to look at our data. So inside this data, we have our input and our output, because we're doing a classification or supervised learning. So there's the input images along with the labels. And our input traditionally gets assigned to a variable capital X. That's a very important difference. Capital X gets our images, and our Y gets our labels, lowercase y. So inside this, we'll have our images. Oh, by the way, if you want to, let me if you want to say run your own code or like play around with the variables, if you hover your mouse over in between a cell and click the code button, you can type in whatever you want. So I can type in X. It's gonna print something like, yeah, it's gonna print crazy stuff. But that's if you want to play around with the stuff. Feel free to change it. All right, so we're looking at this. Got our input assigned and our outputs assigned. Let's look at the shape. This is very important. When you import data, look at what shape it is. In this instance, we have 2,000 images. Each one is 80 by 80 resolution, so 80 width and 80 height. And this one here, this is interesting because we're working with X-rays. X-rays are traditionally grayscale images. So this one represents the number of color channels. Sorry, number of color channels. So if we were working with color images, this would be the number 3. All right, next thing, let's look at the shape of our output. Let's see if anyone is there yet. This is task 4. The shape of our output. We've done the shape of our input, and our input is X variable. Let's get everyone to do the shape of their output. I'm just gonna hold back. Got some people catching up. Yeah, we've got the output shape. Yeah. So yeah, we don't look at the shape of our output. And what might the shape of our output be? Well, if we're there's the shape of our output. Our output, because it's a binary classification, the output labels are either 1s or 0s. 1 being, I think I specified later on, 1 being when it's pneumonia, and 0 when it's not pneumonia. So we can actually, if you create a new cell and click like Y, you can see this is a list. Specifically, the first 1,000 are all representing not pneumonia, and then the remaining 1,000 are pneumonia. It's not printing 2,000 here because it automatically concatenates it when you visualize it. But that's the way that's what the Y variable is. So that's storing a list for each of our images. They have a respective 1 or a 0. All right, I'm looking at people's progress going through. We've got most people are up to task 4. We have a couple of people that are stuck on task 3. If you're stuck on task 3, it is this. So make sure you type in pneumonia.obj, and if that's not working, make sure you definitely have downloaded the data. So if you're stuck on task 3, make sure you do that. Make sure you run this cell to download the data, and then you type in this name here, pneumonia.obj. All right, I'm seeing most people now up to task 4, which is our shape. So yeah, y.shape. We did our input shape with X, and we're doing our output shape with Y, just to look at it. And you can see 2,000, a list of 2,000. All right, okay. Critical mass on task 4. We're going to be progressing on task 5. And if you're stuck in the previous one, feel free to like rewind the YouTube video, and then you can see what I typed in for that task. We have that. Okay, so we got actually a really good question. What is OBJ data? That is an excellent question because I did type it in up here as .obj. When I was creating this data set, and actually, I'll show a link to the actual data set. This data set is a pneumonia data set on Kaggle. And it consists of images, raw images as like PNGs and stuff, and JPEGs. And what I was able to do is I will import that into another Jupyter notebook and clean it all up, get them all to be the same size, and then store them in this array structure that we call NumPy. NumPy is like a Python library that we use to store large arrays and matrices. And I was able to take all the images and store them as a NumPy array. And then when I want to save that data set to then re-import over here, I just gave it, you can call it whatever you want. I think because it's a Python object, when I was saving it, I call it OBJ. But the OBJ, the syntax, that's completely arbitrary. This is what we're importing is a Python pickle object, which is like a way of storing any kind of Python variable for later use. So I could have called that like dot pickle or whatever. So I just made obj up. Okay, so that's why it's that. Okay, we're continuing on. Oh, yeah, everyone's task 4. Okay, let's go on to task 5. Got our Y shape. We import our Y. We can see some Ys if we want. Now we're actually going to look at some images. So this is it. So this is what we're all here for. We're all here to look at an image. So we're using the matplotlib library, which is a good visualization library for Python. I'm actually going to make sure that my isn't blocking my. We're using the matplotlib library, and we're just going to get the first image. And how we do that, if you are not familiar with the Python syntax here, this is a syntax used to kind of fetch objects out of lists, because our x variable is actually a huge list of our images. 0 means give me the first image. This colon means get me all the width pixels. This colon gets me all of the width height pixels. And this means get me the first channel. And because there's only one channel, it's just going to get me the grayscale image. So that's because we've got a grayscale image. And this is getting me the first image. And you can play around with this. If you change this number, it will get you a different image. They all look very similar, but I assure you, those are different images. That one's got a little. Yeah, so that's which image. So we're getting the first image. And this is the image. What this is a color map. So by default, this is actually kind of fun. If you print this, like a weird color, that's just how matplotlib visualizes a number between 0 and 255, which is the pixel values we've got here. If we want it to look like an actual X-ray, we'll set it to gray. There's also other like cool color maps. All right, we're checking out here. We got lots of people on task 4. Oh yeah, we haven't got to task 5 yet. Oh yeah, how many images are there? These are some quick questions. I won't fill these in. I want to get you guys, because I've told you all the answers. So yeah, type in how many images, and remember to click play. There's no enter on this. So I'll give you the first one. 200. Nope. 2000. Correct. Yeah, remember to hit the play button to submit your answer. How are we doing for time? We're doing great. We've got full 20 minutes left. All right. Everyone, like, go through, do those answers. Oh, we got loads of people. 5, 6, 7, task 7. Nice. Remember, if you get like really stuck on like task 1 or task 2, you can rewind the video to when I was going through that section. Everyone, most of the people are up to task 8. Okay, cool. All right, we're going through here with the pixels. Let me do that. That was 80 if I remember correctly. And we got here 80. Let's check the Slack channel. Any questions from my PAs? We answered the OBJ one. Okay, cool. All right, height. Cool. How many channels of color? Grayscale. Not falling for that one again. All right. What am I up to now? The corresponding label. All right, so we looked at an image. What does a label look like? These are the ones stored in our Y variable. Well, as I said before, it's a binary. In this case, like, it automatically converts it to a floating point, but that's a 0, even though it's 0.0. But yeah, that's representing normal. Oh yeah, we can see here. 1 represents pneumonia, 0 represents no pneumonia. And 1.0 and 0.1 are the same thing. So the first image is a non-pneumonia image. Remember, the first half of our data set just so happens to be the way I set it up. All no pneumonia, and then the remaining 1,000 images is of pneumonia. That's 9. We're all good here. All right. We're gonna look at the last image. This is a similar syntax before. -1 means get the last element of a list. 0 meant get the first one. And yeah, showing it, grayscale, this is the last image. And the corresponding label for this image is a 1. 1.0, 1, same thing. Now, a fun little task is check like if you can tell the difference between this image and the other image. So that's no pneumonia. and that's pneumonia. I can't tell the difference. So that's why it's a really interesting problem, because it's actually a cool use case where machine learning potentially can solve a problem that even like humans with eyes can't solve. Maybe if you're a doctor, you probably could solve it, but for regular Joes, you can't. All right, next one. What is the label class for the last image? This is. I can't remember what task I'm on. I should really have numbered them. All right, a lot of people got this. Yeah, this is task 9. This is pneumonia. Remember to click the play button. All right, I'll let people storm ahead. Here we go. Let's see how many of each label we have. Yeah, I think I mentioned this before. The first half of our data is all normal images, and the remaining half is pneumonia. And it's a data set of 2,000 images. We have 1,000 of each class. 2 classes, binary classification. And we have a quick summary just to go over what we all just did. So yeah, we imported 2,000 images, 80 by 80. They're all grayscale. 0 means normal, 1 means pneumonia, and it's a balanced data set. So that's a unique aspect about this data set, is that we have exactly 1,000 of each class. That is surprisingly rare in the real world. You rarely get a data set that is like perfectly balanced. And if you remember at the start when I talked about, like the very first time I introduced what training data and test data is, I showed like an accuracy score where it was just the percentage of correct predictions. That accuracy score is fine. You can use that. When you have an imbalanced data set, like when maybe you're predicting fraud, where there's only 10 like cases of fraud versus like 10,000 cases of normal behavior, that accuracy metric will start to like screw up, because if your model just predicts everything to be normal, it's gonna, the accuracy, like it got 99% of them correct. So we're working with a balanced data set here, but that the very first metric I talked about, which was accuracy, that doesn't work very well with imbalanced data sets. But precision recall does. So that's the cool thing about getting to know precision recall, because you can use precision recall in imbalanced data sets. All right, so we've got that. Now we're doing that train test splitting thing I mentioned at the very start. Very important for supervised learning, because we want to test our model with data it's never seen before to really work out if it learned something. And see if we've got any questions. Nope. We're continuing on. We're going to import the libraries we're using to build our neural network. In this case, we're using Keras. A bit about Keras: it is like a high-level library for building neural networks. We're not going to go like really in depth as to how it works and what all the layers do, because it's kind of out of scope for this. But we might do another virtual one where we do go into depth about what these layers do. But for now, we're just going to gloss over it. It's building a neural network to predict images. Given an image, tell me 1 or 0, or a number between 1 and 0. So although we're not going to go into depth about what each layer does, you can see a few things that you might be familiar with. Like, we're telling it our input shape is 80 by 80 by 1, and you might catch on that is the shape of an individual image. So we have 80 by 80 pixels by 1 color channel. And you can imagine if you had a bigger image, these numbers would be different, or if you were working with a color image, it would be 80 by 80 by 3. So that's one thing to keep note of, is just the input. And then a cool thing to keep note of is the output. We're just outputting one node. So one node in a neural network will output a number between 1 or 0. So yeah, that's our neural network. We're gonna make sure we run that. Don't forget to run that. And then we're gonna compile it. Again, we're not gonna go in depth of what all these things do, but at the end, you're free to come to the hangout and chat about the neural network and what it was about. All right, first question: what is the input to our model? Let's see. I can't remember what task this is. Am I teacher? I'm on task 10. Okay. Let's answer this one. What is the input to our model? Task 10. Wait a bit. We got people coming through. Success. Everyone doing good. We got very good. Yeah. Yeah, there we go. 10, what is the input to our model? So everyone got it right. I discussed, yeah, so if it was a color image, it would have 3. But it's not, it's a grayscale, so we know it's gonna have 1 as the last one, and the resolution is 80 by 80, so you can see there, that's what it says there. 80 by 80 by 1. Cool, that's our input. What is the output? This is a good one. So let's see if everyone gets this one correct. What is the output to the model? I can't keep forgetting. Oh, everyone got it right. I thought this would be more of a trick, but I guess I went over enough times. Like, it's not always exactly 1 or 0. It's going to be like a number in between. So yeah. The output to our neural network is actually a number between 0 and 1, inclusive, because it can be exactly 1, but that's like very, very rare. If it gets like perfect signal going through the network, actually, if it's well, actually I won't go into it, but if you test it with an image from its training data, that's when you're likely to get an output that is exactly 1 or exactly 0. That's it. But if you're testing with data it's never seen before, it's likely to be a number between. All right, there we go. Correct. Onwards. Now we're doing train a model, so it's going to take a while. So we're going to see task 12. See how many people have trained a model. Just get it. There's nothing to explain here. It's going to be using our training data to do like what I said at the start, what supervised learning is doing. It's all about finding the pattern between our training data and our output data. Remember, this is the we ran that function that would split our x and our y, and this was the output of that function. So it gave me an x train, a y train, and an x test and a y test, which are all kind of splits of our data. So it's just gonna look at the x train and the y train when it's actually trying to learn the problem. And then what's nice about this Keras API is that I can also tell it my test data, and it will, every time it like does that kind of pass of learning over our data set, it will also test itself on the test data. But it's not going to try to learn from the test data. It's just going to do that. So then it can tell us what score it got. It's a very honest network. It doesn't cheat by looking at the Y test data. It will test itself, and then we can see here what it got. So the first pass, okay, it got about 80% accuracy. And the next, okay, almost 90%. Okay, cool. Hopefully you got numbers similar to this. If you ended up getting numbers that were like 0.5, that's a problem. But the kind of thing with neural networks is there's a lot of randomness built into them. So that might just be a weird state it got into. So feel free to just like refresh, like rerun, make sure you rerun this, the defining of the network and the compiling of the network, if you get stuck into this like 0.5 accuracy score. But if you get something like this, like an 80 or a 90, that's what we want. All right, so we've trained our model. Let's see how many people have trained the models. Oh yeah, loads of people have trained the model. Okay, great. We're gonna go on to looking at the performance of the model. So yeah, this is actually plotting the performance as it's training. So we trained it we call it 2 epochs. That's 2 times it went over the training data and adjusted itself. And these were the scores. So the training data was data it was seeing and was adjusting to, and the test data it didn't see. But actually, funny enough, it was doing better on the test data, which is just like chance. Like usually what happens if you're training for a long time, the training data, it will start to do better on that because it's kind of like it's learning the answers more closely. But because we're only training for 2 epochs, they're similar enough. All right. Got that. I'll check any questions. All right, we're gonna be making a prediction now. So let's look at an image. In this case, we're just looking at the shape of the image. So it's an 80 by 80 by 1 color channel. If we want to make a prediction, it just so happens that in Keras, we have to pass the model a list of images. Like it's kind of silly when we want to make a prediction with 1 image, but it makes sense when you're making a prediction on like 10 or 20 images, which oftentimes it has to do when it's training. But if we just want to make a prediction with 1, we have to feed it a list. And how we can take our image and turn it into just a list of 1 is by calling this function. Like as I say here, like it's silly, but it's necessary. So I'm gonna do that. You can see what it does. It changes the shape to turn it into a 1 by 80 by 80 by 1 color channel. That's one image that is 80 width, 80 height, and 1 color. It doesn't change the data at all. It just like puts it into an empty list. All right, we'll look at this image and then we'll call that, we'll paste all of that we just did up there into the model.predict. And what do we expect it to output is, all right, we're getting like, we got a question there about 64 versus 32 on the convolutional. Yeah, that's the neural network thing. We can discuss that at the end. But when we make a prediction with this, what's the output? Well, the output, oh, it's actually very close to 1. Again, not 1, not 0. It is a number by default between 1 or 0. Okay, what do we interpret that as? This is the prediction output of the model. This is the next challenge. How many people have passed this one? We're asking, yeah, what is the prediction output of the model? Our options are decimal number, either 1 or 0. Yeah, I feel like I've asked the same question like 5 times. I would put it as a decimal number. Correct. The output. Now, as I showed in the slides, built into Keras, there's a predict classes function which will actually give us a 1 or a 0. So in this instance, like try to, based on how yours predicted, try to like guess what classification is, because mine will get a different result from yours because there's a bit of randomness every time you run it. So let's run it. Okay. Interestingly enough, this is very interesting. So you get a warning. Don't worry about the warning. You can see the output at the end. But what's interesting about the warning is that it's pretty much saying that this predict classes thing is being deprecated. Like it's not going to be part of this API anymore. And what I believe is the reason of that, and it kind of tells you here, is like you shouldn't be using this predict classes because it gives you this default 0.5 decision threshold. And I think what they're trying to do is they're trying to encourage everyone to start thinking about their model and start specifying their own decision threshold. Because I guess when you start specifying your own decision threshold, you start thinking about the problem more, and it kind of makes you a bit more conscious of, okay, what decision threshold do I really want to use? So I think that's why they're deprecating it, because it's a very simple function, but they're saying no. If you're gonna use Keras API in the future, please take the time to think about your own decision threshold based off of your domain application. So that's nice that they're getting people to like think about that. But you can see that I predicted 1 because yeah, mine was over the default decision threshold, which is the next question. What is the decision threshold that is used in this function? Let's see see where people are at. This is a task 14, the next one. Getting all the answers. Yeah, everyone's entering them. Good work. People are getting it right. Oh, we got one person. Very good. All right. Yeah. All right, almost everyone's done that. Yep. So the default decision threshold is a nice and simple 0.5. Awesome. Okay, let's compare what our model made against the actual output. All right, the actual answer was 1. My model predicted 1, so that was good work on my model for this example. Hopefully yours got it right as well. If it didn't, like try running the training step to train your model even more. But we'll come back to that later. All right, now this is where we get fancy with the visualizations. What I did, if you remember my slides, I showed a little diagram of our emojis plotted along all the threshold outputs, or all the signal outputs from our neural network. And I'm actually going to do the same thing here. So yeah, each line represents a single test image, and depending on the output that came from the neural network, that's where the line is. So for example, there's loads of images here where we passed it in and it came out like close to 1. So those are the ones where it's predicting pneumonia, and lots down here where where we put an image in and it came out as a 0. And those are the ones that are predicted normal. And then there's kind of like this, there's a bit of sparsity in the middle, which makes sense because as it's learning, it wants to optimize to get all the ones that are pneumonia to be predicted as 1, all the ones that are 0, or all the ones that are normal predicted as 0. So there's going to be this natural kind of dispersion happening in the middle. It's really going to try to push everything to the side. It's kind of a cool effect. Like if you run the training some more, you can see this spread out even more, which is pretty cool. But for now, we don't need to do that. In fact, it helps if we don't run the training more and see this spread. So we have that. Let's see if there's any questions about that. Okay. Now we'll visualize. There's no need to input anything here. It's just like running the code. Remember to hit the play button or shift enter. We'll visualize. Let's show the classification. Run. Right. Go down here. Bam. So I didn't change anything. I ran the same prediction, except this time I actually kind of colored in the labels. So you can see on the right-hand side of the 0.5 threshold, they're all predicted as pneumonia, and the left-hand side is all predicted as normal. You can see that. You can see the threshold. We don't. Well, I do know, but I haven't visualized it. The true answers to these. But we can just see what the neural network is assuming. Like it's guessing that these are all pneumonia. But we're gonna look at a confusion matrix now that will tell us how well this is actually doing. So let's do that now. We're gonna run the confusion matrix. We're gonna import some functions that are gonna help us visualize it. And this is it. This is the big one. Here we go. So what is going on here? So this is the same confusion matrix that I showed earlier. I have set it up to be the same orientation, so all the predictions are happening vertically, and all the true answers are happening horizontally. You can see here, when it's predicting pneumonia, it's actually pneumonia like 250 times. But there's some where it's predicting pneumonia and it's not pneumonia, 15 of them. This is where we're predicting it to be not pneumonia, and there are actually pneumonia ones. So there's 50 here. What does that mean, like versus what we just looked at? Well, it means like somewhere in here, there's 50 pneumonia cases on this left-hand side. And what does it mean for this number 15 here? Well, it means when we predicted pneumonia, 15 of them were actually normal. So somewhere in this area, there are 15 normal images. How do we know? It's because our test data. So that's remember the thing. Our test data, we know the actual answers. That's why we're using test data. So we know for certain there's 15 here that shouldn't be here, and there's like whatever it was, like 40 here that shouldn't be here. All right, now this is the big one. This is where it gets so wordy. So let's all try to get through these. See where I am at. There. Okay, everyone's going through those. Yeah. Take your time. What is the top left quadrant? So this quadrant up here. So these are the ones where we're testing positive for pneumonia. And as we can see from this slightly misaligned label on the left-hand axis, they were actually pneumonia. So positive and correct. Positive and correct. True positives. Next one, what is the top right quadrant? Oh, everyone's whizzed through these. Top right quadrant. We are testing, as you can see, the prediction is normal. So they are predicting negative results for pneumonia. And they were incorrect because they were actually pneumonia, as we can see from the horizontal. So that is going to be a false because it's wrong, and negative because it is predicting it to be negative for pneumonia. Bottom left. Close. Oh god, we're close to the time limit. Okay. Apologies if this has run over some people. Happy to stay or leave. We're just at the end here. Bottom left. Oh, I've got to go through this. Bottom left. Bottom left. That is positive for pneumonia and wrong. So that's a false positive. False positive. Okay. The bottom right, I just remember it's the true negative because it is testing negative and it is actually correct. All right, we're almost at the very end. All right, let's calculate precision recall. These are the equations for calculating precision recall. I kind of explained them with words earlier, where it was like, oh yeah, the precision is how, what percentage of the time when we're predicting it to be positive, is it actually positive? This is where it gets incredibly wordy, and it would take ages to go through this. So like, go through this at your own time. In fact, I'm going to paste a link into the chat. And this is an interactive confusion matrix, which you can play around with to help build up the intuition around the precision recall. So let me paste that into chat. I think this is useful. So play with that on your own time to help build that intuition between the relationship between precision and recall. Because yeah, it's an insanely wordy topic, so it would be unfair to assume you can just like pick it up immediately. I'm still confusing them, as you can see. Right. Next thing, how do we change that threshold? We talked about it a lot. Well, because it's an if statement, I've programmed the if statement into this visualization here. So I need to zoom out a bit. Here we go. So let's drop it down. And we can see, keep an eye. So yeah, you can see the threshold change. It's now predicting all the ones just down here to be normal. Try to keep track of the numbers in these quadrants. So let's say we want to optimize for recall. We want to capture as many pneumonia patients as possible. If you remember, we needed to lower the threshold. So if we lower this, let's see this number here. So we're focused on increasing this number as much as possible. So it's 276 now. Let's lower that. 283. Right, and you can see this went up. So the number of falsely predicted for pneumonia went up. See the trend. Okay, let's try to minimize this number. Let's say we do not want it, like we don't want to accidentally predict people to have pneumonia. So what do we do with that? Well, we can move that up. Let's move that up to 0. So this dropped a lot, but you can see that did hell with our recall. And that's an important thing. The trade-off between precision and recall, they literally trade off with each other. And it's also an important point that how you define your problem can potentially flip whether you want to optimize for precision or recall. Like if I said, instead of predicting people to have pneumonia, you predicted people to be like healthy, then it would flip all this stuff. That's where it gets like super confusing. So yeah, it's important to like very cleanly define what your problem is, and from there you can work on optimizing for either precision or recall. Let's drop that. Okay, last bits. If you wanted, okay, this is the. So yeah, I'm not gonna actually. I'll go through this. See how many people got through this bit. Yeah, almost everyone. Yeah, this is an interesting question. It's a fuzzy answer. There's no like perfect answer to this. But let's go through it. If we wanted to absolutely minimize how many people you falsely diagnosed. What's good about this, I've forgotten the answer to this, so I actually have to work it out. If you wanted to absolutely minimize how many people you falsely diagnose having pneumonia, what decision threshold would you use? Okay. Falsely diagnosed as having pneumonia. So this is the false diagnosing, this quadrant here. So that's them having pneumonia and that being wrong. So that's the falsely diagnosed as having pneumonia. I'm just going to play with this because I forget. Let me lower this threshold and see what I get. Does this go up? Okay, that goes up. So if I want to minimize this number, I've got to increase my. Go to 9. In fact, let's go real crazy. Let's go to 1. See what happens. All right. Okay. So something interesting has happened here. We went to 1. Why not? The option's there. It has just set it to 1, so everything is being predicted as normal. Technically, our precision is perfect. Like it's not this is at 0 and it's not false, but you can clearly see like this is no longer a machine learning model. This is not just a catch-all if statement. So a score of 1 isn't going to help. 0.9 seems good. Like we minimize those. Yes, we get a lot of false negatives, but the task was to minimize the false positives. So a high threshold. Let's enter in a high threshold. 0.9 worked for me. Correct. All right. If the negative impact of false positives versus false negatives was roughly equal, what decision threshold would you use? All right, so if we wanted to kind of just balance the number of false positives versus false negatives, intuitively, you would think a balanced threshold. But you can kind of play with this one and be like, okay, if you really did want to balance it, you would be somewhere in there, like, although I'm kind of, okay, that technically 0.3 in the way that I trained my model would balance those. But if you train a model long enough, a decision threshold of 0.5 should give you a balanced trade-off between false positives and false negatives. In this instance, I guess it completely depends on your data and the model you're training with, how you get a balance between this. And you would use this exact tool, like a confusion matrix, and a way for you to monitor the effects of the threshold. So yeah, in this instance, it actually, for the way I train my model, a 0.3 would give it a balanced one, but balanced threshold gives you a balance. All right, how do you deploy this? Well, you would run the predict statement and put whatever threshold you want. That's it. It's built right in. In fact, it's going to pretty much force you to do that in the future when you can no longer call predict.classes. And that's it. You've done it. We've all completed it. Or most people have completed. I can see here. Excellent work. We're now I'm gonna stop the stream here, and I'm gonna drop into the chat, and then we're gonna create a Google Hangout where people can hang out. But also, we're gonna be distributing a Google form in the Slack to get like feedback about this. So make sure you please like fill that out. All right, I'm gonna shut down the stream now. Thank you all so much for staying to do the notebook. Hopefully, we'll have a couple of you stay for the Google Hangout, as many as you want. But yeah, stay safe, take it easy, and yeah.